Hello. Hi, everyone. My name is Milo Phillips Brown. I'm a philosopher at Oxford, and I'm delighted to welcome you all today to discuss revisiting the impossibility theorem, fairness in practice. Okay, very good. So we are going to move pretty quickly. We've got 5 10-minute talks to cover in an hour. I'm going to go rogue and give us 2 minutes, give us the 2 minutes that we lost at the very beginning. So to the speakers, I'll indicate when you've got 1 minute left and also when you have 3 minutes left. And so without further ado, let me introduce Andrew Bell. Thanks.
Okay, test. So, hello everybody. Welcome to this presentation on the possibility of fairness, revisiting the impossibility theorem in practice. And I'm Andrew, and you can see we have a long list of authors here. But I want to give a special mention out to 2 of the authors, Nazar and Tanya, who were collaborators from the Ukrainian Catholic University, and they were part of the NYU Responsible AI Summer Research Program with Ukraine in 2022. And they did amazing work in unimaginable circumstances. And actually, Tanya is even here today. And Nazar really wanted to come and did a lot of paperwork, but unfortunately, because he's fighting age male, it was hard for him to leave. But he's attending online and everything. And yeah, I just want to give a special shout out to them, and actually maybe even a round of applause for their work. And now, returning to the paper, so I'll start with some background and motivation about the impossibility result. So for many of us here, we're probably familiar with this idea of fairness metrics in algorithms. So over the past decade, researchers have developed dozens of different metrics that measure the fairness of predictive algorithms in different ways. So you might be familiar with terms like equalized odds, disparate impact, or the disparities between the false negative and the false positive rates. And if we converged on anything, it's that fairness is highly context dependent. And none of these definitions are one-size-fits-all definition. And there's often contexts where we may want parity between groups for 1, 2, 3, 4 more of these metrics in order to meet the fairness criteria of that circumstance. And sort of through this exploration came the impossibility theorem, what we kind of colloquially know this fundamental result by. So Kleinberg et al. First found that one cannot simultaneously equalize calibration within groups and the balance for the positive and negative classes outside of 2 special cases. The first of these is equal prevalences, or base rates, you may know it as, the percentage outcome of the positive class. And the other is if you have a perfect predictor, and these are kind of the only 2 exceptions right now known for the impossibility result. Koldakova defined a near equivalent result for classification and represented it as the relationship between the false positive rate, FPR, the prevalence P, the precision, PPV, and the FNR, false negative rate of the classifier. And while these are important fundamental results, and they're strong mathematical results and theoretical results, theory does not always translate to practice. So there's an increasing number of studies in fair ML literature that are kind of showing this. And so one recent example is by Rodolfo et al. And was in Machine Intelligence that showed that it's not always necessary. They show 4 different case studies where it wasn't actually necessary to sacrifice any accuracy at all to ensure fairness. And I think as a community, we're still trying to parse out why this is. But one of the reasons is that practitioners are not always thinking about equalizing these fairness metrics in the same way that we are in theory. So one example is that we often don't need to ensure exact parity between metrics. So if you have the false positive rate for one group is 10.132%, we often allow some kind of margin of error there. It could be like 1%, 2%, or 5% margin of error, depending on the context. And what this work really is about is kind of exploring, if we do allow this margin of error, is it then possible to satisfy these seemingly incompatible fairness metrics and kind of get around or circumvent the impossibility result as we know it? And one way that we can kind of think about this is a thought experiment. So one of the most pervasive examples of racial disparity, systemic racial disparity in education is the racial achievement gap, in which black and brown students graduate from high school at a rate that's 10% less than that of white students. And so in this case, if we're building algorithms for predicting student performance, there's kind of this baked-in 10% base rate difference that we can't get around. And the question is, if we allow some margin of error between these fairness metrics and they have this 10% base rate difference, can we actually satisfy these seemingly incompatible fairness metrics? And the answer of this will come at the end of the presentation. And so we explored this result by looking at what we call the fairness region. And I have to note, our paper is very dense, and I really defer you to look at the paper, and unfortunately I have to gloss over a lot of the details, but I will try and hit some of the high-level ideas. And so what we really tried, one of the ways that we explored this fairness region is by reparameterizing the impossibility theorem, but allowing relaxations for each parameter. So down at the bottom of the screen, I have kind of 3 examples where we say instead of precision for one group has to equal the precision for another group, we add this epsilon margin of error term. And once we do this and we kind of reparameterize an approximate impossibility result, then we can sweep over all these different values of tolerances and we can actually graph a fairness region. And so that is what is shown on the left here. So this is a fairness region when you have a 20% base rate difference between groups and a 5% margin of error. But so what's important about this? Each point, each blue point in this graph is actually a model, a feasible model that is satisfying these fairness constraints within a 5% margin of error. So these are kind of getting around the impossibility result in this way. And this was kind of hard to conceptualize or understand what to do with, so we took this analysis. It's also very difficult to get the size of this area because it's ripe with nonlinearities. So we then took this a step further and implemented a constraint program to try and enumerate all these solutions. For those unfamiliar, a constraint program is kind of like a superset of linear programs that allows you to enumerate over a set of solutions given a constraint. And I'll focus first on the graph on the left. So on each of these axes, we have different group prevalences. So you could imagine like a majority group and a minority group and their prevalence within the data set. And in this case, we don't allow any margin of error difference. So this is like world under the impossibility result. And you can see that solutions only exist along the diagonal when the prevalences are equal to each other. And this is what's given to us by Kleinberg. But if we then allow this 5% margin of error, you can see that there's a much more dense space of solutions. And in fact, if we kind of quantify over all the sums of these, if we have a 5% margin of error, we get 10 times the number of possible solutions. So these are, again, all valid solutions that are kind of getting around the impossibility result within this 5% margin of error. We also ran some experiments on real-world data sets to try and prove the existence of some of these models. And so, again, I have to defer to the paper for a lot of the details, but we basically used a linear program and some really complex mathematics behind this that is able to find at least prove the existence of at least one of these models. And we looked at 5 different data sets. Just quickly, I'll call your attention to the first one. This is actually a data set, open data set from Ukraine, and Tanya's kind of like the resident expert, so if you're looking for more data sets, you can talk to her after the presentation. But the takeaway of these experiments is that on all 5 of these different data sets and looking at different outcome and sensitive attribute pairs, we were able to prove the existence of at least one of these models that we're finding with the constraint program and the other theoretical results. And I'll just quickly call your attention to this bottom graph where it says fairness constraints, and these dashed lines are this is the margin of error, and you can see that these are the false negative rate, the false positive rate, and precision, and they're kind of staying within the bounds. And again, I defer to the paper for more details. There's also, if you want to run this on your own data set and prove the existence of some of these models on your own data set, there's also this tool available. So again, I know this was very dense, and we even acknowledged this in the paper, and we kind of tried to formulate our discussion in a way that was digestible. So we actually formulated as guidance for practitioners. So what does all this mean for the community? What does this mean for the people building models that are actually going to affect people? So if you're going to allow some kind of margin of error between the metrics, we find that the size of the fairness region, i.e. the number of feasible models, the number of feasible models is affected by 4 different factors. So the group prevalence values, how close they are to 50%, the size of the prevalence difference, the classifier performance, and in the case of a resource constraint problem, the size of a resource constraint K. And generally, we observe that the closer your prevalence values are to 50%, the smaller the prevalence difference, the better the classifier performance, and the smaller the resource constraint, you have more opportunities to find these fair models. So returning to our original thought experiment, based on our observations, if you have a classifier that has a precision above 75%, you should be able to construct a fair model with these 3 fairness constraints within this 5% margin of error on this data. And lastly, I want to end with some other broad takeaways. So the first one is that I think one of the main findings of this paper is that slight relaxations in these fairness constraints actually result in an abundance of solutions rather than a scarcity. So you saw just by having a 5% margin of error, you have 10 times the amount of opportunities of finding a fair model. The second one is this idea that accuracy and fairness are actually not necessarily in conflict. And this is supported by a lot of kind of other emerging literature, which is actually a more accurate model has more chances to be fair. So in some cases, if you actually improve the accuracy of your model, you may also be able to improve the fairness of your model. And lastly is this idea that achieving fairness along multiple metrics for multiple groups and without sacrificing accuracy is likely much more attainable than we currently believe. And we may be actually self-imposing some of the implications of the impossibility result and limiting what we can actually do with these fair models. And there's some recent work by Sue et al. In NeurIPS that kind of is to this effect as well. So hopefully the community can go in this direction and we can try and build even more fair, more robust models. Thank you.
Great. Thank you. Mary Beth de France is our next speaker. Yeah, come on up.
Hello everyone, I'm Mary Beth. I'm a first-year PhD student at the University of Ghent. I'm sorry that my recordings are still on the slide, so please ignore the circles with my face on it. It's for the online presentation. I thought they were gone with exporting them to PDF, but PowerPoint didn't listen to me. So today I'm going to present my paper, Maximal Fairness. Thanks to the previous speaker, I can skip a little bit of my introduction, which is also about the impossibility theorems, as I guess nearly every paper in the session will start with a little bit. So I'm using kind of a different names than the other presenter. So I'm using equal opportunity, predictive equality, and predictive parity. So instead of the false negative rate, the false positive rate, and the positive prediction value, these are just names that I prefer to work with. They have the exact same meaning, but they're just nicer to work with, in my opinion. So again, the works of Childechova and Kleinberg et al., they all investigated the combination of these 3 metrics, and they all actually found that the third metric is impossible. But in proving that the combination of these 3 metrics together are impossible, they actually also proven that the combination of 2 of them are possible. And that's actually where our work focused on. We're actually looking at, okay, so we have this combination of 3 fairness metrics. These are not possible, but what combinations are possible? Do we need to stop? Because we have found that these 3 are incompatible. Maybe we can find a different combination that does do what we would want it to do. So how did we do this? We actually used the confusion matrix for this. I know this is a little bit different than most authors did. Most authors use the probability, but there's actually an advantage for us using the confusion matrix because one of the metrics that we use is actually solely defined on the confusion matrix and is not defined in probabilities. So that's where this extra flexibility comes in. In the paper itself, we also made one slight adjustment. Normally, when you talk about a confusion matrix, you have the absolute values. We actually reduced them back to percentages. This didn't have any real effect. This was just a lot easier to do our math with. Okay, so we have this confusion matrix. I think most of you might know it. So it has the true positives, the false negatives, and everything of your system. So we have 4 variables, and say we have 4 groups. That means 2 times 4 variables. However, we have already mentioned it. We have our base rates in the system. which actually already constrains 2 of them. So if we have 4 variables per group, 2 are already constrained, so we can like think of them as sliders. We can move 2 sliders around, but that's it. That's our constraint, so we have 2 per group. So that's kind of the area we can play in. And then we can have all our fairness measures. So these are the fairness measures we used in the paper. These you might know of different ones, but these are the ones we found in literature and we thought might be interesting. So first of all is demographic parity. I think most of you know this and have used this. This is one of the more prevalent ones. A slightly different one is equal opportunity, and it's a little broader predictive equality. I'm not talking about equalized odds because that's the combination of the 2, and we only looked at the most fundamental ones, but because we are combining them in a later step, we also are talking about equalized odds in the paper, but not explicitly. Then we move on to a kind of a different one, that's this predictive parity, and then it's neighboring one false omission rate parity. We named this one because it didn't have an official name yet. And overall accuracy equality, it might be something that a lot of people don't think about when talking about a fairness metric, but it's actually, I still feel like if you have an accuracy of 80% for one group and an accuracy of 60% for another group, I don't think that you can call your system fair if it has such a discrepancy of performance. So that's why I always also include it as a fairness metric. And then the final one is the treatment equality, which some of you might not know, and that is actually the rate of false negatives compared to false positives needs to be equal across both groups. So that's a kind of a different one. You can't express this in probabilities or in statistics. It's only on the confusion matrix defined. And so that's how we solved it. So how did we then actually solve it? Well, it was the tedious task of combining all of them in a set of linear equations and solving all of these linear equations. So it was kind of a tedious task. So we have our 7 metrics. And from that, we could actually see that the combination of 2 metrics was always possible. So this has 2 implications. One, from these 7 metrics, you can actually say, okay, these 2 are the 2 most important things in my setting that I want to satisfy, and you can just try to find a system. Currently, there aren't that many techniques, but I'll talk a bit about that later. But these are always feasible. You can always satisfy 2 of these together, and that's also kind of logical because we still had the freedom in our confusion matrices to have this room to play with, to have the 2 of them. The only situation in which that would have not been possible if they would immediately contradict each other. And that would have been kind of strange that we have a fairness metric and then we would have a different fairness metric which would say the complete opposite. So fair in one situation would then mean that it's not fair from a different perspective. So that's not the case. So that's a very happy thing that all of our current fairness measures don't contradict each other. But then when we are going to the combination of 3 fairness metrics, things do get a little bit snug. We only have 5 of them. So out of all the 7, so out of the combination of all 7 metrics, only 5 of them actually are possible to combine. And we can actually also see that the result of Kleinberg et al. And Shuldechova isn't present in them. So it is very constrained, but on the other hand, we still have in the entire room for all the different ones. It's also important to note that the combination of 4 metrics, it also isn't possible. So we also investigated it further. And we could actually see that from the confusion matrix, we kind of already expected that we didn't have the freedom for it. But then through the math and through the sets, because you can see it's actually just a set theory with the way we describe it here, you can't find a combination out of the 3 that we have that you could create one of 4. So that's kind of sad, but we know now this is the space that we can constrain ourselves to. Now, why did I do? No, I'm not going to put that up. Now, why did we do this research? Currently, I'm finding it a little bit sad that we see the impossibility theorem, and we feel very constrained about it. Like, we have this combination of 3 fairness metrics. Oh, that's not possible. We're going to stop right here. And then if you especially look at a lot of techniques to mitigate fairness measures, they always focus on one of them. And it's also one of the very popular ones, like treatment equality is often forgotten, a lot of things, but it has its merits too. So I'm kind of hoping that with this work, it kind of emboldens people to, first of all, maybe try and make a method that can enforce some fairness measures on a system, but with the flexibility of, oh, I need this fairness metric in this system and that fairness metric, and try to impose it, but also give more room to play with it. And that hopefully we can also start the discussion of what is a fair system, and maybe we can start that discussion with what fairness metrics do I want to impose on that system in order for it to become fair. So it was kind of like more a conversation starter as a paper, and to relive the impossibility theorems, which have been dormant for quite some years. So I would like to thank you for your attention.
Okay. Before we do the third paper, I have some good news, which is that we have a Best Paper Award for our next talk. So would you please come up? This is Alessandra Calvi. Her co-presenter is not here, but here we are. Very good.
Okay. Now we have so much pressure.
That's right.
Okay. So yes, full screen mode, I think. Yeah. Hello, everybody. Okay, I want to anticipate that I am a better writer than public speaker, so please forgive me in advance. So my name is Alessandra Calvi. I am a PhD researcher in the Law, Science, Technology and Society Research Group of the Vrije University at Brussels and in the DPA lab, and also in the ETIS lab of CY Sergi Paris Université. I have a legal background, but since a couple of years I've been pursuing a PhD in law and computer science, and today I'm here to present a paper that I co-authored with my co-supervisor, the computer scientist Professor Dimitris Kotsinos, entitled Enhancing AI Fairness Through Impact Assessment in the European Union, a Legal and Computer Science Perspective. So before talking about the paper, let me just briefly introduce the concept of impact assessment to you who may not be familiar with it. So in general, impact assessments can be defined as evaluation techniques that are used to analyze ex ante, which is translating to, say, before, possible consequences of an initiative for relevant societal concerns that can be, for example, privacy, data protection, the environment, ethics. Societal concerns are matters of interest. So the point of impact assessment is, on the one hand, to support informed decision-making from the entities that carry them out, and also the second objective is to protect the societal concerns. Specifically, algorithmic impact assessments can be defined as iterative processes that are used to investigate possible short and long-term societal impacts of AI systems before their use, but with an ongoing monitoring and also a periodic revisiting even after their implementation. If I have to summarize the main argument of our paper in a nutshell, is that, when these algorithmic impact assessments are conducted in a participatory and transparent fashion, they would allow us to contextualize fairness and therefore to reconcile the multiple definitions of fairness that exist in legal, social, and computer science domains. So as regards our research method, we carried out a desk analysis, we consulted legal and computer science literature, European policy documents and regulation, and so on. And as regards our position in relation to existing work, like other scholars, we consider fairness as a socio-technical issue that needs to be addressed by adopting a multi- and interdisciplinary perspective. We share the idea that algorithmic impact assessments and other forms of impact assessment can be used to develop better or fairer AI solutions. Nevertheless, contrary to the majority of social scientists, we remain open to the use of fairness metrics. We are aware that they have been criticized under several points of view. We admit that they are not perfect, but still, in a context of impact assessment, they could be used to contextualize fairness. Therefore, we defend their use in this specific context. From a legal point of view, we provided to innovative contribution. We tried to propose a classification of fairness metrics under 3 legal instruments existing or under discussion in the EU legal framework, that are the General Data Protection Regulation, the Digital Services Act, and the Artificial Intelligence Regulation proposal. And then we compare 3 types of assessment that are foreseen under this regulation, that are the Data Protection Impact Assessment, the DSA Risk Assessment, and the Conformity Assessment under the Artificial Intelligence Regulation proposal. We also briefly mentioned the Fundamental Right Impact Assessment that the European Parliament has proposed to introduce, but it's in the appendix. So first of all, I will, fairness in the legal social science domain. Okay, I will not enter into details about the slides. We just provide an overview of the multiple definition of fairness that exist in social sciences. We propose to link the concept of fairness to the idea of social justice to overcome a narrow understanding of fairness that normally exists in the legal sector that tends to equate it to non-discrimination. And also we focus on the specificities of fairness in the context of European data protection law, because their fairness is a general principle of personal data processing. It's not defined in the GDPR, and nevertheless, the European European Data Protection Board and other European regulators have tried to define it. One aspect that was linked to fairness that I think is quite interesting in the concept of impact assessment is the principle of no risk transfer. So in principle, companies should not transfer risk on their clients, user, and so on. Fairness in computer science, also here I will not enter so much into details because the previous speakers have done it. So we provide a brief overview of group fairness metrics. We analyze them, also the legal and ethical principle that underpin them, and we propose a classification of fairness metrics under the 3 regulations that I mentioned. We concluded that to some extent, fairness metrics can be considered state-of-the-art technical measures that controllers need to implement to demonstrate compliance with the GDPR. And also, to some extent, we can even argue that the GDPR mandates their adoption because they are among the most advanced techniques to prevent discrimination. Also, they can act as risk mitigation measures in the data protection impact assessment and in the DSA risk assessment. But perhaps most interestingly, they seem essential to comply with the requirements set under Title 3, Chapter 2 of the Artificial Intelligence Regulation Proposal. And that's why we consider that this type of conformity assessment is not just a technical exercise, but the choices performed in that context could have quite important impacts on the life of people. So we then provide an overview of algorithmic impact assessment. We emphasize its advantages and drawbacks. Also now I will not enter too much into details, but a point that I want to raise is that normally algorithmic impact assessments can be merge with the precautionary principle, and this means that, for example, if a certain initiative, if the risks related to certain initiative cannot be sufficiently investigated or limited, an initiative could be blocked. They have also important drawbacks. They can be time-consuming, lead to bureaucratization. They bring about risk of participation washing, and also they are not legally binding in the European Union. This is the main problem. And that is why, since algorithmic impact assessment in the European Union are not currently legally binding, we shift our attention to other types of assessment that are currently or will be legally binding and are nevertheless expected to influence AI developments. They are indeed the data protection impact assessment, the DSA risk assessment, the conformity assessment, and the fundamental right impact assessment, maybe, if ever it will be approved. Okay, so we analyze them under several points of view. I will not enter into details about our analysis, but you can find it in the paper, also in the appendix, a bit more extended. And our conclusion is that, although to different extents, all these assessments would allow us to discover possible short and long-term societal impacts of impact assessment. So what does it mean for algorithmic impact assessment? Perhaps in the future, these algorithmic impact assessments may evolve as integrated impact assessments, and they will involve different actors depending, for example, on the phase of the AI life cycle, on the type of data involved, on the legal framework applicable, and so on. Therefore, open questions remain. For example, who are the actors that will need to be involved, their responsibility, also who are the entities that will supervise them. Also, there will be 3 procedures that will be in place, so this raises questions in terms of coordination and information exchange. Also, the different approaches that could be chosen in terms of public and expert participation, because the 3 processes that we analyzed have very different rules about that. Also about the revisiting of the processes, because as I was mentioning before, they are not just one-off exercises, but they need to be revisited. And also something important, it's about transparency, to which extent these algorithmic impact assessments will be public. And last point, it's about the access to remedies, because normally, so far, there is no possibility for the public to access remedies in relation to violation to impact assessment, and instead we contend that this option should be given. So, as regards our conclusion, we showed that there are indeed different legal and regulatory tools that could be used to promote fairness, on the one hand. On the other, also there is an effort in the computer science community to understand and measure fairness, and these 2 goals appear compatible and can be combined. However, we want to stress that further empirical research is needed, for example, about the societal impacts that fairness metrics can have in different contexts. On the other techniques that can be used to ensure fairness, as well as their role in the assessment process that we mentioned, as I was referring to before, the possible loopholes as regards the coordination information exchange, the effective suitability of impact assessment to improve policy as regards AI to positively affect AI development. And also another problem that needs to be addressed is how to ensure meaningful participation of both the public and the expert in these assessment processes. So with this, I would like to conclude. Thank you very much for your attention.
Great. I would like now to welcome Lane Harrison.
So before I begin, I want to thank the team that put this together, particularly Hilson Trace, the PhD student first author who couldn't be here. He's with his family in Nepal. Unfortunately, Kathleen Catchell is here, the second author, and I'm the last author, Lane Harrison, which means that if you have any hard questions, please ask Kathleen. So I'm excited to be at FACT because I think this community does a really great job of conceptualizing and defining and measuring fairness and developing metrics that can be then translated into toolkits, and then occasionally those might make their way into visualization systems that further operationalize them. Visualizing fairness and working with fairness is not new. Here are a couple of systems, primarily from the visualization community, including some of our prior work on the bottom left, the FairFuse system, which deals with fair consensus rankings, which we'll interrogate a little bit more in this paper. But in this paper, what we explored were a couple of, kind of issues at the intersection of visualization and fairness. So one, we wanted to figure out if some visualizations could aid fairness tasks, but perhaps hinder others. Some of these metrics are complex, and the visualizations for them are complex, and it might require people to reason about fairness in complex ways. So we wanted to investigate that. Second, we wanted to kind of ask how fairness should be visualized. There are a lot of techniques in the visualization community, sometimes tightly linking with the underlying data, particular visualizations of a given metric, or using coordinated multiple views where you might have a fairness space and a data space and interacting in between them. And then finally, we wanted to see if visualizing fairness could potentially be misleading or otherwise reduce agency. And we do this through a controlled experiment where we have a system that uses fairness metrics and visualizations, and another system, an equivalent system, consensus views, that has none of that. And we'll talk about how they're different in a second. But the FairFuse system, the kind of problem space that we're working in is fair consensus ranking. So in this case, we can consider a group of students. These students may have protected attributes. We would have then some rankers, maybe math, reading, and writing teachers who have ranked these students. Maybe they're being unfair to some of the students. We don't know. But there would be a consensus ranking. There are algorithms, metrics for generating that. And FairFuse is kind of built with this type of problem space in mind. Now, to achieve fairness, we resort to some metrics. So a couple of those being the favored pair representation, which measures the fairness of each group in relation to each other, the attribute rank parity, which looks across the entire ranking and looks at statistical parity, and finally the pairwise disagreement loss, which looks at the base ranking in the context of a consensus ranking and measures the difference between them. And as a visualization person, I get really excited about this because these are complex metrics, and it gives us an opportunity to explore how to visualize them in the context of an interactive system. One thing that we wanted to offer is a goals and activity analysis, and the paper at the bottom defines what this is, but a goal and activity or a goal and task analysis in the visualization community is sort of a systematic process for looking at a particular problem, in this case consensus ranking, and defining the goals that the people might have in such a context, absent of any way of actually visualizing them. So we're not thinking about visualizing in this case, we're thinking about the goals that people have. We can then think about the underlying data and activities that people might want to perform on those data or task on those data, and then we can take this and sort of define our visualization system and potentially our visualization evaluation, and that's what we did in this study. Now, quickly, just some of the main features of Fairview, so you're familiar. We have the stakeholders rankings visualized on the left, a consensus ranking on the right. This view right here is the group fairness view. So this is a completely fair set. Now we've got the students visualized. You can see their positions. And we actually have some fairness metrics visualized as well. So we have over-advantaged students on the top, under-advantaged students on the bottom. The little dot is the FPR score itself. We added that line to show the distance. And then if we look behind, we can see the ARP, which is this shaded area, which shows the distance between the most advantaged and the least advantaged group. So we just situate these on top of the visualization of each of the sets. Now we also, for PD loss, we have this similarity view, which we're using a matrix representation where you can look at all pairs in relation to the consensus view as well. So we take Fairviews and we perform what one reviewer called an ablation. And I didn't know what that was, I had to Google it. But an ablation is where you kind of delete some things from the other thing. So that's what that looks like. So we took some of the fairness metrics out of consensus views. We took the similarity view out. And this is actually kind of representative of what Fairviews looked at while we were brainstorming about how we visualize fairness in the first place. We also, last thing, we take out the fairness slider because you could tune the algorithm, and that's not something that people can do in consensus views. Now, our study design was a between-subject study. We had training phase, we had 8 tasks, and we also added in an open-ended fair ranking task to sort of, give people a scenario to work with at the end. It's a little bit less structured. The task here, I think what we want to say about the task is that they map to particular activities. A given task might map to a particular activity, which then would map to an aspect of the visualization that a person could use. And importantly, we made sure that the consensus views system actually had, full capabilities of performing the exact same task. We were very careful about the wording of the task to be fair to each system. So let's go through these tasks. So tasks for the participants, rather than go through each one, I think it would be helpful to think about them. We had ranking exploration task, we had fairness-oriented task, we had consensus representation and analysis task, and then finally the open-ended fair ranking analysis task. And each of these had, accuracy metrics that we could associate with them and sometimes qualitative responses. So here are the results. We were happy to find for the ranking exploration task that there was basically no difference. And that's what we would expect. This is a positive control where basically the visualization components are essentially the same. You do have the presence of the fairness metrics and visualizations that might be distracting, but these are essentially the same, which is great. Now, we see real differences in the fairness-oriented task. If we ask a participant to identify over-advantaged race groups, Fairviews just kind of blows it out of the water. The consensus views does very poorly in this type of task. Identifying particular groups, identifying which of the 3 rankings is most unfair, identifying the ranking that most advantages a particular group, and all of these Fairviews outperforms, but it's interesting in the last one. Consensus views actually comes close. So participants could actually reason about fairness using without fairness metrics and visualizations. It was just a little bit more difficult. This is an example of that. So you could see in the Fairviews, if you wanted to find the most 2 advantaged race groups, you just have to find the high dots. On the bottom task, you actually have to read these dot plots and kind of do a mental averaging to figure out where they would be, and that can be a little bit lossy. Now, the consensus representation and analysis task was an interesting case. Neither performed actually well. Fairviews did perform a little bit better, but this is where qualitative analysis really saved us. It turns out some participants were getting the correct answer, but they were using the wrong metric for it. They were supposed to be using the visualization on the right, the similarity view. They were using the visualization on the left and looking at ARP, and it just so happened in this case that ARP correlated with the correct answer. So that gave us, from a visualization design perspective, something to kind of worry about. Now, finally, we had the open-ended fair ranking analysis task. This was where we asked people to construct a fair ranking. And we look at the ARP, which is like the overall fairness of the rankings, lower is better. We look at the PD loss, how representative was the resulting ranking of the underlying base rankings. And we can see some patterns here. We can see that, okay, Fairviews helps people be more fair. But the PD loss is pretty much equal between them. The interactions are about the same. And this visualization wasn't that helpful, so we did what good visualization people do and looked at it a different way. So here we've actually plotted every step of every participant. So each 100 participant, you can sort of see the lines that people take and where they started. And when we put those together, we draw a couple of observations. One, everybody started with a relatively high ARP score because they all started at the same spot. The mean ARP, so fairness, is largely improved in fair fuse. It's not improved as much in consensus fuse. And a few people in consensus views were actually really good at getting a high fairness score, but they totally lost representation of the base rankings. And when we talk about managing a multi-objective problem, that turns out to be very difficult to do, and we might need human-in-the-loop algorithm tools to kind of help us navigate that. So I'll leave a couple of takeaways here, some helps and some hinders. So if we're developing fairness where algorithms, we should allow people to tune fairness, because it turns out that users, even crowdsourced participants, were able to operate with that well. But we should be wary of a hindrance. So displaying fairness metrics might really lead people to rely on them a bit too much. One help is that properly designed visualizations of fairness metrics really do help people in fairness-oriented tasks. They took to these immediately with very little training, and they were extremely accurate with them. However, if you don't design it well, you can lead people to misleading conclusions, and they're using a metric that's not even designed for the thing that they're trying to do. So we have to be careful at the same time. So we talk about some limitations in future work, but in the interest of time, thanks.
Okay, our final speaker in the panel is Samuel Bell.
Hi everyone, I'm Sam, and today I'm really happy to be talking about our paper, joint work with my colleague Levant. Simplicity bias leads to amplified performance disparities. So there are three motivating questions for this work. The first is that we're interested in which parts of the data set a model will find difficult, and whether or not we can identify that ahead of time. The second question is whether this concept of data difficulty varies between model, i.e., can we say whether data difficulty is model specific? And the third question is, if you accept the idea that data difficulty is model specific, what if data difficulty aligns with something like demographic information? So crucially, for point number 3, I'm not saying this is something that's intrinsic or innate about different demographic groups, but we're interested in the model's view of the data. What if a model just finds one group harder than another? So for a little bit of background, we have converging evidence that certain models have a preference, an inductive bias for simple. We call this the simplicity bias. It means they tend to learn simple functions before more complex ones. And it also means they tend to rely upon things like lazy shortcuts instead of learning what we'd intended them to. But what we're interested in is how this notion of simplicity bias might interact with a model perceived complexity difference between groups. So when a model finds one group more complex and another simple, how does simplicity bias come into play? So just to give you a concrete example, let's take a look at this example data distribution on the left, which had colors on it a few moments ago, so that's going to be a little bit difficult to explain. Okay, so I'm going to try and do this anyway. Let's just imagine we have this data distribution. This is meant to be a binary classification task of solid triangles versus hollow circles. And if you were to imagine drawing a line across at y equals 0, we would imagine there are two different groups there. On the top, which we would call a more simple group, there should be a linearly separable decision boundary. But on the bottom, we have a nonlinear, more complicated decision boundary. So again, just to reiterate, we're not kind of saying that this distribution represents something fundamental actually about the different groups, but instead it could be some sort of function of data quality, a function of pre-processing choices, or you could imagine it as something like pre-trained embedding quality, each of which are known to vary along demographic lines like geography already. So Other colors here, yes. Okay, so just to make this more clear, imagine the top half of the example distribution is on a blue background, and the bottom half of the data distribution is on a red background. That should hopefully help things. So in our work, what we do is we first train one model on each group separately. So we train a model on just the blue group, the top group, and a model on the red group separately. And we might get test accuracy curves that look something like these dashed lines, where the blue group ends up with higher test accuracy than the red, more complex group. We call this gap during single group training estimated difficulty disparity, here marked as D tilde. And again, before we move forward, I'd just like to note that what we're doing in this work is we've chosen to operationalize data difficulty, or this notion of difficulty via test accuracy, but it's plausible that we could have chosen a different metric there, relevant to a different task. Subsequently, we then train a model on both groups together. This is called conventional training that you might be familiar with. And we also observe a performance disparity, which we call observed difficulty disparity. At this point, really what we're doing is we presented the model with a choice of which group to prioritize. To achieve an increase in accuracy over the whole data set, it could choose to prioritize the simple group or the complex group, or both equally. If the model chooses to prioritize the simple group at the expense of the complex, we see an increased observed disparity relative to what we estimated from single group training. When we see this observed disparity greater than estimated, we call this difficulty amplification and link it directly to simplicity bias. To test this out for real, okay, and there's a background here, great. To test this out for real, we're going to show you our key experiment designed to isolate difficulty amplification in a controlled environment. So in this experiment, our data is group balanced, i.e. both groups have the same number of samples, and there are no correlations between group and label. So the model can't leverage anything it knows about group information to infer anything about labels. The experiment follows the same setup as the illustration I presented before, with simple and complex groups on blue and red respectively. And in our experiment, the way we construct this distribution is we stitch together classes from CIFAR100 in order to create a kind of artificial delineation between a known simple group and a known complex group. So on the top, you might be able to see that the decision boundary is between aquatic mammals and flowers. They're very, very easy to separate. Whereas on the bottom, you see two different types of mammals that are harder to separate. And these precise classes are chosen based on the actual test accuracies of a ResNet 18 model. They're not based on human intuition as to what might be difficult. So if we were to train a model on this task, we would expect to see that the easier group outperforms the more complex group in terms of test accuracy. And this is exactly what we see in the central figure, here marked by the solid lines. But we're more interested in the gap between the two lines, i.e. the observed difficulty disparity, here marked as the black solid line in the rightmost figure. Most importantly, this observed disparity is above the dashed line, which is estimated disparity. So what we're seeing is the model does indeed find one group more simple, but then it doubles down. This is evidence of difficulty amplification as a result of the simplicity bias in a controlled experiment where we can't attribute this to a majority-minority group imbalance or to an over-reliance on something like spurious correlations. Subsequently, we can repeat this experiment by drawing many different versions of this task and evaluating different models, such that in this case, we're plotting observed difficulty disparity as a function of estimated difficulty disparity. So you can see on the left figure, in the blue line, we have a lower performing model, LeNet, which tends to attenuate the amplification. And in the orange, we have ResNet 18, which tends to amplify. We call the slope of this line amplification factor, or K. We can repeat this over many models, and we see a figure that looks something like this one here, where if we're selecting models based on overall accuracy on the test set, the models we would tend to choose are those which amplify difficulty disparity further. So the most important point to take away from this figure is not which models amplify, but the idea that model choice really matters, and that performance disparities aren't just a function of the data, because they're model specific. We also evaluate the effect of other design decisions. Just to highlight two here, on the left we look at network width in a ResNet 18 in order to evaluate the effect of parameter count or capacity, finding that increasing width tends to decrease amplification. And on the right we have the effect of training time, where we can see amplification factor peaks early during training before decreasing slightly to a plateau. And we interpret this as evidence that seemingly innocuous design decisions, such as whether to use a common regularization strategy like early stopping, might indeed be harmful and further amplify performance disparities. To turn from our synthetic task to a real-world data set, we're going to present two very briefly present two practical case studies. First, for demonstration purposes only, we train an age classification model on Fairface, disaggregated by race annotation. And while Fairface is already reasonably balanced, we explicitly rebalance it using subsampling to, again, exactly match the number of samples between groups and to match the distribution of ages across groups. So once again, there's no way to use information about race annotation to learn anything about age annotation. And we have no figure, which is a nightmare. So what we'll do is I'll just describe the concept of this figure, which is that what we see in this experiment, we see, as you might expect, is the point of my talk, that observed disparity is higher than estimated disparity, which we interpret as evidence of difficulty amplification and simplicity bias in action. Very briefly, in a second case study that also wonderfully has no figure associated with it, we do a similar kind of experiment where this time we're doing a multi-label object classification task on Dollar Street, this time disaggregated by household income. And this time what we're seeing is we see higher observed disparity than we estimated between the highest and lowest income quartiles. So I'm sorry, you'll have to use your imagination, or actually this is a great call to read the paper. So just to draw a very quick couple of conclusions, the most important point that we think is inherent in this work is that performance disparities can emerge even when you have fully balanced groups, and in the absence of spurious correlations between group and label. And that's how a lot of evaluation of things like mitigation strategies is often conducted in this space. So it's not enough to just fix one's data set, and I'm sure we all know that in this room. Our second main conclusion is to suggest that commonly used models, those used by those that have the highest overall test accuracy, can further amplify for performance disparities because they over-prioritize the groups they find simple. The amplification factor itself is model-specific and varies by both architecture and various design decisions. And we'd like to highlight that difficulty disparity and difficulty amplification are both evidence of the complex interplay between data, model, and optimization method, and argue that investigating any one of these without the others is likely to be an incomplete account of what's really going on. Through our sort of imagined case studies on Fairface and Dollar Street, we also demonstrate this complex interplay has a practical and real-world impact that in our case studies manifest along disparities along lines of both race and household income, respectively. And with that, I'll just say thank you very much.
Okay. If I could actually ask all the presenters to join me on the stage, and for audience members to please come to the microphone here. We've got about 7 minutes for questions, so for everybody, if you could keep it short, 1 question per question, that would be great.
Hi, thank you all for your talks. My question is for the last speaker whose name I didn't catch. I'm wondering if or how you accounted for model capacity. So if, I guess I could imagine if you train them separately, you can achieve perfect accuracy on multiple groups. Maybe then training together you get no disparity. I guess how do you think about model capacity?
Yeah, thanks for the question. So, I mean, just to answer the pre-question, we get perfect train accuracy in every case. It's the test accuracy that varies. I think in terms of how do we think about capacity, so one of the examples that we present there is the effective network width, which we're just using as a proxy for parameterization or capacity. And interestingly, what we see is that, increasing capacity tends to decrease amplification. So that's interesting to us, particularly in light of previous work that suggested that increasing network capacity or increasing width increases an over-reliance on spurious correlations. So there's a kind of different form of bias that seems to have the kind of exact opposite effect. And we quite helpfully interpret that as evidence that what we're seeing here is not down to spurious correlations. It helps to disambiguate the two. Thanks.
Hi, my name is Jamel. My question is for Mary Beth, I believe. Great talk, very interesting. I guess I was wondering if you could expand on, it seems like your argument is that the confusion matrix is well suited versus probabilistic methods, and I think I was just wondering if you could further explain that choice and that distinction that you were making.
Yeah, so, well, what we're saying, so everything that you can say in a probabilistic manner, you can actually also start applying to the confusion matrix. So that's why it's, for us, like, you can go either way, but for certain metrics, such as the treatment equality, which is just the false negative to false positive rates, you can't actually express something like that in probabilistics or in statistics, which is something that the confusion matrix holds. And for me, I didn't start from a statistics standpoint of view when I started all my research, but more the really computer science thing. And I find it more natural to actually just think in terms of the true positives and false negatives and stuff like that, because that's, for me, I always envision real people behind those numbers, real cases being affected, and I feel that for me is why I always prefer to work with that, because it feels more real with the numbers that I'm working with, instead of like the precision is that high, but then I need to start translating a lot of things, while the false negative rate, that's someone that got a bad decision and got less opportunities because of that reason. So I think most of the things that we did could be done through probabilities, but I mean, also the way that we solved all of our equations was just way easier on the confusion matrix than I needed to start doing with probabilistics. As you can see in the paper, I have about 20 pages of appendix in pure calculations. So that's also why it made our life a little bit easier.
Okay, thank you.
Also a question for the last speaker. So for calculating the estimated disparity, you mentioned that you trained two separate models for the easy and the hard group, but it was not very clear to me how you separated between the two groups in the first place. Could you please elaborate a little bit on that?
Yeah, great question. So I think in, for example, the case with C400, where that's our sort of like key experiment that we build upon later, we design the task explicitly by stitching together classes, and two of the classes are easy to separate as observed on a ResNet 18. Like, we train a model to do all these binary classifications, and two of them are hard to separate. And then we create this kind of rather arbitrary synthetic task, but we do that because then we know some of it's easy and some of it's hard.
Sorry. And how would that translate?
Wait, we've got time for just one more question. If somebody has a question for a speaker who has not yet fielded a question.
Yeah, I have a question about the visualization presentation. It should hopefully be really quick. When you're doing the comparison between consensus view and fair view, and you're talking about how consensus view was able to approximate closely in like the last of your 4 projections about which racial group was preferred, did you obfuscate the racial delineations to ensure that it was based on the visualization as opposed to prior societal knowledge?
Are you saying whether we had labels for?
Yeah, so basically like the question was like which was preferred, and the answer was like white. But like if you have societal knowledge, that might be something that you bring into that as opposed to just like the visualization itself. So I was wondering, was it obfuscated from the reader, or was that?
No, it wasn't obfuscated, but that's actually something that we're looking at a follow-up study, is when you do that, does that impact how people are processing these visualizations?
All right, cool.
All right, everyone, thanks so much. Please join me again in thanking our speakers.